then it will take some of these important registers and put them on that stack, right? And the important registers happen to be all of these, R3 to R0 and XPSR, return address, LR and R12. Once this has happened, it is going to set the program counter to whatever the interrupt number index in the vector table is pointing to.
Hmm.
So let's take a look at the programmer's model for the M-class CPUs, and then try to cover the concepts like what vector table is, how does the Cortex M4 boot up, and memory map, and how it handles the interrupts.
Yeah.
And yeah, go ahead, Rajat.
So again, Piyush, I would like to reiterate the thing that so what we are covering over here is the minimalistic model that the person needs to know. There's much
Right,
more in the Cortex M devices,
right,
and that we'll cover as part of separate videos where we'll go into the depth of each and every portion of the Cortex M, and we'll visit these things in much more details. While
right.
these are the minimalistic things, let's say you are working on Cortex M and you are not very much interested looking into the details of the CPU itself. Your main focus is working on USB, etc., or
Mm-hmm,
middleware, but you
mm-hmm.
still would like to know how the CPU boots up, how the CPU works. So
Right,
this will give
right,
you an overall idea or pointers to search beneath.
right. So we are essentially saying that we'll only cover the essentials,
We'll only
so
cover
that
the essentials.
right. And if people want to like deep dive, then they can, either
Yeah,
follow other videos that we'll make or go to the
yeah,
documentation. Okay,
yes.
fair, fair. I
The
think that's
resources that we mentioned in the slides contain references to if they
Mhm.
want to go into much more depth of it.
Sure.
Yeah. Okay.
Okay, perfect. So let's start off with the idea of vector table. What is it?
Yeah. So whenever we talk about CPU, how does
Mm-hmm,
a CPU? So the biggest question that when you're learning CPUs, you should ask, how does the CPU boots up? How does the
mm-hmm,
CPU know where should I start executing? You
mm-hmm,
know, and so there are multiple portions around it.
mm-hmm,
So the CPUs usually have something called a vector table, or either it is a vector table or it is a
mm-hmm.
fixed. It is always a fixed address where they are going to boot up.
Okay, okay.
So the idea of vector table is that it defines CPU has a lot of things, right? It has a location where it wants to boot from. Then it has exceptions and interrupt handlers when we talk about vector interrupts.
Mm-hmm.
So the vector table actually tells it's a offsetted table that
Okay,
tells CPU if for example the vector table address is this, CPU knows that X position from vector table is this. And it is
okay,
a
fair.
group of addresses. It is basically a table of addresses that are important to CPUs.
Okay, so in this case, then what we are representing here is a vector table,
It's a
and
vector table.
right, what you're saying is that each entry in this table is an address.
Is
So
an address.
some number like something like so. So this
Yeah.
24 here would be an address in the memory.
Yes.
Okay, 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 fair.
So, and these addresses can mean different things to CPU, and CPU has been designed to understand these things innately. For
Okay.
example, let's say if a usage fault happens, what
Mm-hmm.
CPU knows only two things. One is an offset register, which is called vector table offset register in ARM,
Okay.
VTOR,
Okay. Vector
that basically
table
defines the
offset.
base address of that vector table, where that vector
Okay.
table is located. And then it
Mm-hmm.
knows that if there is a usage fault, I need to access entry number 8 or 7,
This one. Okay.
this
Okay.
one.
Right.
And what CPU will do now is take this address, load into PC, and start executing from that location.
I see. So you're saying whatever happens to be the address here,
Yes,
if the usage fault happens, then the program counter will equal to this value, and then
yes,
somewhere in the memory at this address, the ABCD address, there would be some code. It will start to execute that.
yes.
Okay. Okay. Perfect.
So that's where the concept of vector table in ARM comes from, and
Mm-hmm.
why it is offsetted and not fixed every place. And this is a very important thing to understand.
Mm-hmm.
So whenever we talk about our typical applications, right?
Mm-hmm.
So our typical applications usually contain a bootloader, a application, a kernel, So
Mm-hmm.
let's say you want to maintain. So if we consider bootloader and application as separate entities, because they are two different applications running at the same time, and
Right.
you want to handle interrupts differently in each position. So what you
I
can do
see.
is you can offset your vector table according to the application you are in. So when you are executing bootloaders, you can have your VTOR fixed within the bootloader memory.
Mm-hmm.
And while
Mm-hmm.
you start executing the application, you can change this VTOR to now
Mm-hmm.
have the vector table in the application memory. And you can handle the same interrupts differently based on your application.
Understood. So what you're saying is that we can maintain two memory regions, two vector tables essentially, you know,
Yes,
and depending on who is currently executing, they can set the VTOR to this or this. So when application is running and let's say the usage fault happens, then the handler that is stated here, the memory location that is stated here, the program counter would be set to that and that specific code will be executed.
yes,
So essentially bootloader and application gets to install and handle the same interrupts differently if they so
yes.
wish to.
So
Okay,
this
fair.
makes both these application independent. The bootloader development doesn't have to rely on application, and application development doesn't have to rely on bootloader.
But they do have to kind of, over another channel agree on the VTOR values. The fact that they are not using the same number,
Yes,
that
yes,
much needs to be communicated.
yes, yes.
Okay, and what is the default value for the VTOR then? Because I'm
Uh,
assuming even before
So
the bootloader sets it.
don't want to go into much more details
I see.
for
Okay.
this VTOR. But I will still give a highlight. So as
Hmm.
per specification, it should be zero, but it is not usually zero. It is up to designers. And what
Mhm.
happens is there's something which is very transparent to users called a boot ROM,
Mhm.
and boot ROM can decide this VTOR value ahead of time and come to
I see.
bootloader. So for a user, VTOR may not always be zero. It may turn out to be some memory location.
I see.
And we will
I
look
see.
an example of it when we start working on our kit,
Okay. Okay.
and that the VTOR is not always zero. It is
Okay.
usually VTOR is the you usually place the VTOR at the
Mhm.
place where you want to start executing your code.
I see. So wherever your code sits, the
The
VTOR would
first
be
section should be
pointing.
a VTOR,
Understood.
vector table register, vector table,
Understood.
and
Understood.
you
Understood.
load the VTOR with the starting address of that memory.
Correct. But we would not load, essentially. The user
Yeah,
won't.
somebody. So it's the responsibility of the previous firmware to make VTOR the correct value for the next firmware.
Okay. Okay. Hmm. Cool. I
Okay.
think I'm understanding this. Um, okay. So anything else that we want to talk on this slide?
I think we will look into these exceptions one by one as we move into
Okay.
much more practical labs. What these
Mhm.
exceptions usually mean,
I
uh,
see. I
but
see.
I guess it is fine right now.
Okay, maybe I want to call out the attention to this one fact that the 16 exceptions here are fixed,
Yes,
right? So these are internal CPU state related or bus related, system related, but things above number 16 would be interrupts.
yes,
And these are like coming from peripherals, timers, this, that, all of that. And
yes,
these can vary depending on which vendor you're buying your Cortex M from, but the 16 are always fixed.
yes,
Okay, perfect. So shall we go to the next slide then?
yes.
All right. Okay, so what's happening
Yeah.
here?
So now we know the what vector table is. We would like to understand how does Cortex M starts booting up. So
Mm-hmm.
we discussed in the past. So whenever if you want a device to boot up, you need two crucial things. One is the stack pointer that the device should use,
Mm-hmm.
and the second is the program counter where it should start executing.
I see. Right.
And when we look at our vector table, the first
Mhm.
two entries of our vector table are the stack pointer and the reset vector.
Right.
So when the device boots up, this VTOR will be a fixed value, and the designers have to make sure that there is a vector table over there for ARM to pick up. So
Mm-hmm.
what ARM does is it looks at that vector table offset and read two words from there.
Right.
It loads the first word into the stack pointer,
Mm-hmm.
and then it loads the second word into the reset vector.
Right.
And now that the second word that it loaded goes to the program counter, and now ARM has both the values that it needs to start executing, and ARM will start executing from there. This is
Hmm.
what we call the reset handler.
Right. So this region here, right? So
Yes,
all of this then is the reset
handler.
handler.
And
Okay.
now the control flow is within the programmer's hand. Now hardware,
Right.
whatever control flow hardware should have has been gone up. Now it is completely in the hands of the programmer. Programmers
Right.
can from this reset handler jump to wherever they want.
Understood. Understood. So all the computation, like the application, will be running in the reset handler.
Yes.
Right. Okay. Okay. Fair.
Yeah.
I should mention, based on what I know, so the M class CPUs operate in either, the handler mode or the thread mode,
Thread mode.
right? And I suppose the reset handler is the only handler that runs in the thread mode.
No, it executes in handler mode.
It executes in the handler mode.
Every exception will go into handler mode. You have
I see.
to exit from there into main to go into. You have to.
So okay, this is an interesting point. So what you're suggesting then is that the reset handler would be executing here, and we have to make a transition to the thread mode.
Yes, to my understanding, yes.
Okay,
Um,
fair.
reset handler in ARM in thread, or it's an interesting question because now even I'm thinking,
Sure,
since we
maybe
are
we can
going into
revisit
main,
this.
then main means
Hmm.
then that means the main keeps executing in the handler mode, right?
Yes,
Nobody
exactly.
has switched it for
Thread mode. Yeah.
thread mode.
My hunch is that the reset handler executes in thread mode, but we can revisit that. We can, confirm our understanding
Yeah,
also.
we can confirm
And
and come back to it. My
yeah,
understanding
yeah.
was that everything and every exception and goes into handler mode.
That is what my understanding was also. And I
Okay.
suppose I somewhere stumbled on the fact that reset is that exception, reset handler. But
Uh,
anywho, I think we can
but it
also
makes
leave it to
sense.
our
But it makes
hmm,
sense if reset handler doesn't starts in thread mode, then all the application will keep on going into handler
running in
mode.
handler mode. Yeah. But
Okay.
okay, since none of us have like a concrete, evidence, let's just
Yeah.
default to rechecking this.
Yeah. I guess we can check it.
Right. And we'll
So
update
there is a
our
way we
audience
can
as
we can go into we can breakpoint into reset vector and look at the status registers of ARM
well.
whether
Fair,
it is
fair,
thread mode or a handler
fair.
mode.
That's a good experiment to do. Okay, perfect.
Okay.
Right. So,
Yeah.
anything else that we want to comment here?
No, I guess it is fine.
Okay, I just want to reiterate so that we establish a base for the next slide. So, what we are saying is there are two things that are required for the processor to boot and operate correctly: stack pointer and program counter. The VTOR would be set to some address by the designers or the boot ROM writers, right? And that will be pointing to the memory region where the vector table is available. Then what you suggested was, as soon as the CPU gets the power, it will go ahead, check the vector table and pop out two words. And the first word will go to the stack pointer. So whatever value happens to be here is used as the stack pointer value.
Yes.
And the next word, whatever that happens to be, is where the program counter will point. And that happens to be the reset vector. Then it will jump and start to fetch instructions from whatever program counter is pointing to. And that's how
Yes.
the CPU has booted now. Perfect. So
Okay.
moving on to the next slide. Okay, memory
Yeah.
map.
So now the next question comes is how does CPU know what to access, right?
Hmm.
So CPU is executing, and let's say you want to set up UART. How do you
Hmm.
set up UART?
Hmm.
Means so I usually like to see the memory map. So this is my ideology. I don't see 32-bit registers as 32-bit CPUs as that have registers of 32. I
Mhm.
usually think 32-bit CPU means you can control 2 to the power 32 signals.
Oh, okay, okay, okay. I see.
So you can manipulate 4 GB worth of signals.
Or you can generate 42 GB worth of combinations
4
out of
GB
the
worth
30.
of. Hmm.
Sorry, 4 GB worth of combinations out
Yes.
of the 32 signals.
Yes.
So these are not signals, these are combinations.
So usually what CPU designers do is
Mm.
whenever they want to have certain signals to be manipulated by the users, they
Mhm.
provide an interface called registers.
Mhm.
A user interface, that's what we refers to. So whenever, yeah, you look at any of the UART IP or any IP in your microcontrollers, they will
Mhm.
have certain set of user registers where you
Mhm.
have certain bits. If you set enable bit, that will enable, the status bit will tell you what
Right.
basically it
Right.
is. Those registers are combination of the signals
Hmm.
internal to the UART. So when you write en bit to 1, what you are actually doing is setting a input, or maybe setting an input of the AND gate to 1 so that the clock starts going into the UART and it starts operating.
Right. So something like so, let's say.
Yes.
Right. So you have the clock here, and then this bit comes from this place.
Yes.
So if you set it to 1, then this is 1. And then whatever the clock is, that will come here, and the UART gets the clock.
So now how do you manipulate this signal? Okay, you have
Hmm.
provided an interface. So the CPU only understands memory, right? It only understands addresses, two things: addresses and values.
Right.
So
Right.
what the designers will do, they arranges these all things hierarchically so that they have a memory address.
Hmm.
And I like to compare it like, so if you know older days, we have something called pin codes, right? Zip code.
Hmm. Hmm.
Whenever
Hmm.
you want to send something, you mention a zip code over
Right.
there.
Right.
So what actually happens is, the mailing company looks at the zip code and sends it to the biggest area they know,
Right.
and then at that big area, that parcel is given to the postman, and
Hmm.
postman starts looking at dissecting the addresses one by one. It
Right.
dissects the address, goes to that area, and
Mhm.
maybe if he knows the address locally, he will directly go to address. Else, if it is an unknown address, what it goes is, it goes to the main area, find someone, ask us, do you know where this address is?
Hmm.
The person may not know the direct address. If it knows the direct address, you will get the address. Else it does, I don't know this address precisely, but I know this street. Why not you
Hmm.
go to that street and ask someone else?
Right. So
Then
it's
the
like
postman will go to that street, ask somebody else, and finally the parcel arrives to the location.
right. So you kind of submit it to main hub. From there,
Yes,
it's dispatched to the smaller hubs. From there to still smaller hubs, and then to the postman, and then
yes,
postman to the destination. Right.
yes.
Okay.
So
Makes
CPU
sense.
kind of does the same thing. So whenever
Mhm.
there is an absolute address, what CPU does
Mhm.
is, CPU just broadcasts it to the next known address where it knows this address can be. And
Okay.
let's say, for example, if we look at this address A84004,
Mhm.
CPU first transmits it to the biggest address it know, and over the bus mat, and it finally reaches the bus matrix, which has an offset of A all zeros.
Oh,
Now,
so
bus matrix says that I may not know this final address, but let me broadcast it to the next major location I know.
actually, I mixed it up, Rajat. Let's do this again. So you were saying that this line here is
Yeah.
the address that the CPU wants to write 65 at, right?
Yes.
Okay, so you're saying this address, then the CPU floats it to the bus matrix, which
Yes.
itself is at this address.
Yes.
Okay,
So
okay.
CPU will broadcast it. CPU will broadcast this address down its stream, and
Mhm.
whoever has this address just accepts it.
I see. So because the bus matrix starts at an A and
Yeah.
there is an A involved here, so
Yeah.
this is sent to the bus matrix, and now the bus matrix needs to figure out how to route the
How to route.
84004.
So
Okay,
bus matrix again tells, looks at its slaves, all the slaves connected to it, and sees,
right.
okay, you which one has a offset of the closing matching offset to it.
I
It
see.
matches out over and sends it the packet.
I see. I see. Okay, so let me actually, for the ease of following this example, write things down here. What you're saying is based on this A, we narrowed, or the CPU or the system narrowed on the bus matrix. Based on this 8 and ignoring all of these, it has narrowed down on bridge 0. And then
Yes.
bridge 0 then goes to the 4000 address in hex. and then within that it goes to the hex 4.
Yes,
Right. I
exactly.
see. I see. So this was like the central hub, which dispatched it to a smaller hub, which dispatched it to a still smaller hub, and then the postman got to this
Yeah.
field. Okay. Perfect. Okay. Let me just erase all of this. Go
So
ahead.
so that's the whole concept of memory map comes in. So that's
Mhm.
why CPU designers like to, CPU designers or chip designers like to, locate everything as a memory location,
I see. And this
because
then,
that simplifies it.
correct. And what we talked about is also called the memory. Let me just write it here. So it's also called the memory mapped IO.
Correct. Interconnect IO, memory
Correct.
mapped IO.
Right. Because you have essentially to this register, for example, assigned an
Yeah,
address, and it behaves as though it is memory because it has an
exactly.
address. But what it
So
really has is signals like these, which are tied to the actual hardware. Okay.
yes, exactly.
Perfect. Perfect. Cool.
So
Okay. Hmm.
if we go to the next one, and that's
Ah,
where we see the whole concept, right? The whole see the everything whichever is connected over there, we connect
mhm,
every designers will place them strategically so that they get
mhm,
a memory, they get an address. So
hmm,
USB peripheral as its own has its own set of addresses. We add a suffix of the bridge, then add a suffix of the bus matrix, and that's where
hmm.
the final memory address of the USB IP comes to the it gets decided by the CPU.
Understood. Understood. Right. Okay. Right. So what we are saying is the range from here to here, for example, is dedicated to SPI. This
SPI.
to this is for the timer and so on. And each of these ranges and addresses are unique. And
Yes.
CPU submits it to the interconnect. Interconnect figures out where to send it
Yes.
from there. Okay. Perfect. Well, this is interesting that the actual real memory is also at a
Yes.
sub address. So if we were to
Yes.
do reads and writes here, then it will actually go to the memory.
Yes.
If we do it here, then there will be a physical world side effect. A packet
Well,
will go out
that's where
or something.
I take a interesting take on memory. I usually don't consider memory as a memory. I usually consider it as a signal trapped in a flip flop.
Ah, okay, fair, 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 fair,
So
fair.
that eases out things for me, that everything is a signal.
Hmm, fair,
Memory just is a signal that is trapped infinitely in a loop.
right. And well, also, I think it is fair to think about, uh, you know, all of these locations as registers or flip-flops.
Yes.
Implementation is different, but you're
Yes.
right that it can be visualized to be like a clogged flip-flop or D flip-flop
Yes.
perhaps, right?
Yes.
Uh, where the value is stuck. Okay,
Yes.
perfect. Moving on then, let's talk about, I
So
see, we spoke about this, but go ahead.
yeah. So now the thing is, it cannot be completely random. Even though you have the memory map, it cannot be completely random because CPU does make some assumptions when it is accessing certain address space.
Hmm.
So if you go back to Cortex M4 architecture, multiple slides back,
Mm-hmm.
back, back.
Still back?
Yes, still back.
Okay.
Okay, we never cleaned them up. So
Yeah.
okay, this slide. So if you look in the M4, M4 has its own bus matrix. If you look at
Uh-huh. Uh-huh. Yes.
down.
Yes.
And this bus matrix is making decision whether it should go to code interface bus or a SRAM interface
Yes.
bus.
Yes.
So it
Yes.
cannot be completely random. Let's say if
Hmm.
you want to, if you want Cortex M4 to transmit it to some peripheral, you have to make sure that the address range is such that the bus matrix routes it to the second bus, which is the SRAM and peripheral interface
Mm-hmm.
bus.
Mm-hmm. Mm-hmm.
And if
Right.
you want it to be instructions, you have to make sure that the memory location from where you are fetching the instructions is within the range so that the bus matrix route it to the code interface.
Makes sense.
So
Makes
that's where ARM comes up with a memory map that it tells to the designers that if you
Mhm.
respect this memory map, I make some assumptions, and these are my assumptions with the memory map. And
Right.
based on it, designers tries to develop their chips that have memory map that respect this address space. So, for example, ARM recommends that the code interface stays within 0x0 to 0x1FF.
Right. You're saying that all of this address range is dictated by ARM.
Is dictated by ARM
So the implementers, the designers have to fit their component within these regions.
within these ranges.
I see. So if I were a designer and I wanted to put, let's say, a UART, I would have to put it within this address.
Yes,
Okay,
within this
go ahead.
address.
Fair. Go ahead.
Oh, so this is the address map, and out of this address map, ARM does take up some of the address map for its own purpose.
Mm-hmm.
Like we saw in the Cortex M4 architecture, there is a external, embed, trace macro,
Mm-hmm. Mm-hmm.
sysdig, nvig, etc. And all of those actually rely on the private peripheral bus.
I see. So you're saying the ARM specific stuff
Yes.
that is part of their own architecture definition, like the NVIC, the SysTick also, I suppose.
Sysdig,
Right.
system control
And
block,
MPU,
MPU,
SCB,
SCB, yeah,
right. So on and so forth will exist here.
will exist over here.
Right. And the implementers are bound to put
Not
it
use
here.
this address space.
Understood. Okay. I mean, okay, you're saying they're not supposed to use this address space because ARM's RTL would have.
Exactly. So ARM's RTL, so if we go back over there,
Mhm.
go back to the Cortex M4 architecture.
Right.
So if we look at the bus matrix, one entry goes back into ARM as well. If we go towards the right and left, there is one entries go back into ARM as well.
Right.
So
Right.
bus matrix is going to route that address space internally, and
Right.
those
And
will
then
never come out on the interface itself.
understood. So they are never going to go out. Or
Yes.
okay. And then this much is what the ARM IP, like if you were to get an Cortex M4 from ARM, then this is what you will get.
Yes.
Okay, okay. And they would have assumed that these peripherals are on that specific address, the private peripheral bus,
Yes.
which is this. Okay, perfect.
I don't
Go
want
on.
to go into the details of external RAM and external device because going into those details need us to go into the details of MPU
Right,
and
and
how
MPU is
MPU,
for another
and
day.
that is a very complex IP of its own.
Mhm.
And I don't want to, introduce the idea of bufferability. I'm just taking the terminology so that
Okay,
if
okay,
people are curious, then they can go and look at it.
right,
But I don't want to introduce the terminologies bufferability, cacheability, gathering, etc. right now
right.
because that
The
is just going to
memory,
confuse it.
right, the memory model
Memory
term,
model,
right.
and
This is
that
for
is
another.
not. People don't need to know that for the very basic purposes of using
Fair,
it.
fair.
And so that's where this assumption of address space comes in. So ARM
Mhm.
assumes this that within this address space it is gonna have X bufferability, X reorderability, and Y cacheability.
Fair, fair.
And that's where the concept of this memory maps comes in, and that's where
Mhm.
it asks vendors to respect this address space because ARM makes some assumption about when it is accessing certain address space.
Understood. Right. So for our purposes, then we would want, or rather, for at least for this presentation's sake, we would want the audience to be aware of code, SRAM.
SRAM.
So this is where you put your code. This is where the data region is, the read-write data region. This is where the peripherals would be, and
Yes.
we are not going to speak about this and this. This is where the ARM Cortex M specific peripherals are. And
Yes.
this is, for the vendor, which we don't care about. Any
Yes.
configuration that the vendor would have will go within this address space.
Yes.
Nice. Okay, perfect. So do we, okay, I think we have just, detailed out the same
Yes.
thing that we spoke here. Okay,
Yes.
perfect. Then moving on, I think we are pretty much at the end of the presentation.
Yeah.
Okay, the
So
exception
we
handling.
just wanted to talk about how ARM handles interrupt, right? So we
Hmm.
looked at that ARM has something called nested vector interrupt controller, a vector table, which it
Hmm.
uses somehow to come up with the address where the handler should be there. So
Hmm.
handler is like a function that should be executed when certain condition occurs in hardware.
Right. And let me also say this, that in M class controllers, the handler is a function, a void
Yes,
function, which doesn't take any parameters and doesn't return anything. And the address of that function is to be mentioned in the vector table.
vector table.
So this vector table, which is pointed to by the VTOR,
VTOR register.
right?
And
So there
one
should
thing
be
to
the
understand
function.
over here is so you don't have to guess where this vector where this handler needs to be stored. The
Mhm.
vendor will tell you which slot in the vector table corresponds to which peripheral.
Right, right.
So
So
when you
this
look
would
at
be
the
in the
data sheet, it will
specification.
tell you that interrupt number 31
Hmm.
refers to timer interrupt. So
Okay,
what you have to do is you have to take the offset of 31 from the external IRQs of the vector table, and that's where you have to store the timer handler.
right. And I should also mention this, that each of these entries are at an offset of 4.
4.
So this entire thing is 4 bytes each.
Yes.
Right. So 31 then would mean that 31 into 4, but then you also had 16 exceptions.
31
So
plus 16 into 4. Yeah.
correct. So 31 plus 16 into 4. Right. That is the address at which you
That is
store.
the address at which you have to store the function address. Function
Yes.
point.
Right.
Function address.
Correct.
Yeah.
And well,
So,
let me just,
yeah,
just so that people, uh,
timer
so
handler.
we have something like so, void, right?
Yeah.
And this is the handler then. Yeah.
Yes.
Go ahead.
Yeah. Uh, so what happens is, let's say you have a timer that overflows.
Mhm.
Let's say you were counting something and it reaches top, which
Mhm.
as per timer IP is an interrupt that should be notified to the CPU. So
Mhm.
what timer does is at this time, and there is some configuration you have to do at the timer side as well, which will look more practically when we jump into the devices.
Example. Yeah. Yeah.
For example, let's just assume that when such a condition happens, timer will trigger a signal to NVIC.
Right.
Now, when the timer triggers some signals to NVIC, this signal to NVIC, and if in NVIC this interrupt is enabled, so you have to
Mhm.
prior enable this interrupt in NVIC. By
Mhm.
default, all these interrupts will be disabled at NVIC level.
Mhm.
And if it is enabled, NVIC will pass this interrupt to the CPU and tell CPU that there is an exception and you need to take care of it.
Hmm. Will it also tell the number? I think it also tells the number.
It also tells the number.
Yes. So there is a
So that
utility.
is a so this is a very internal ARM detail. I cannot for
Mm,
sure know whether NVIC tells the number and then CPU calculates the vector table offset address,
mm,
or
mm.
NVIC calculates that offset address and tells to the CPU.
I see. So based on, the details I know, so there are like two lines going from NVIC. One is the interrupt itself, the IRQ, so to speak, right? And the other one is the number, and this number then sits in the uh, what was that? IPS.
IPSR.
Yes. But
Okay.
again, we can confirm. I can check my sources, but this is a
Okay.
model that has worked for me so far. Okay.
Okay.
Perfect. So
So
IRQ number 31 is conveyed to the CPU.
yeah.
Go ahead.
So when this happens, now the CPU, as we know, wants to actually go into handler mode.
Mm-hmm.
And what we know so far is that handler mode can only access main stack pointer.
Yes.
So if you are in main stack pointer, well and good, nothing will happen. But if you are using the process stack pointer, the first thing CPU will do is switch itself to main stack pointer. And this
Mm-hmm.
will happen internally. User doesn't have to do it. This ARM will
Correct.
take care internally.
Correct.
Now, as the stack pointer is set, the second thing the ARM CPU wants to know is what should be the program counter where I should start executing now. And for
Mm-hmm.
that, it will again go back into the vector table. It knows the offset number 31. It calculates the address where the address is stored, the
Mm-hmm.
vector table entry where the address is stored. It
Mm-hmm.
stores that address into the program counter.
So this will go to program counter.
Right. But
Right.
there's something now you should know. So, but the thing is, if you do this, the context will lose, right? What you were
Mm.
what? So CPU has to do two things. It has to handle that interrupt as well as come back and start executing what it was doing.
Right.
So it should know some context. And for
Mm.
context, I usually like to take an example of a bookmark, right? So whenever you are switching books, you take a bookmark and keep it on a page that you were reading, so that when you come back, you can use that bookmark to know where exactly you were using it.
Right. Right.
And
Right.
that's what is called a context for the CPU. For ARM CPUs, the context is certain registers, a return address, and the status of the CPU it was executing in,
Right.
like the zero flag, negative flag, etc. All these needs to be
Right.
stored. So what CPU
Right.
does is, before it starts executing that handle, it pushes out whatever it knew about the current context into the stack.
Right. And I see that it stores about 8 registers.
Yes.
Right. Okay. What happens to the other 8 registers? I think the handler needs to save them.
The
But
handler
okay,
needs to.
fair. If it is touching
Yeah.
those, it needs to save those. Otherwise,
Yes.
it's okay. All right. And so the context is getting saved on the MSP because that is what the CPU has switched to.
Yes.
Okay. Okay.
So
Fair.
now
And
CPU knows both the things. Now CPU knows the stack pointer as well as the program counter, which are necessary for CPU to execute anything. So it will start executing the timer handle. And once it is done doing the timer handle, what CPU is going to do is going to restore that context. So it knows where the context is. It goes back over there, starts popping out things over there. And if you look at, there's a return address as well as the link register. And link register is used to return back to where it was executing.
right. Understood. So let me actually reiterate all of this because this was a long story. So let
Yes.
me first, get rid of all the marking here, just so that I too many markings. I think we are good. So far, so good. Yeah. Almost done. Yeah. Okay. So I will reiterate what we were discussing. So we talked about the fact that there is a CPU whose context is the registers within, and then there is MSP and PSP, stack pointer shadow registers, and R13 is using one of them usually, right? Normal execution. So you mentioned that there was a timer that went off that signals the NVIC. The NVIC then in turn signals the CPU. The CPU now wants to abandon its normal, not abandon, but context switch from the normal execution to handler. So it is going to move to the handler mode. But before it does that, it shifts its stack pointer to point to MSP, wherever that happens to be pointing. And then it will take some of these important registers and put them on that stack. Right. And the important registers happen to be all of these. R3 to R0 and XPSR, return address, LR and R12. Once this has happened, it is going to set the program counter to whatever the interrupt number index in the vector table is pointing to, right? And then jump to that function, execute whatever is within that. And when returning back, it is going to now pop the context from the stack back to the CPU, restore the value of stack pointer to PSP if it was using PSP,
Yes.
and then continue from where it left off. So
Yes.
essentially, if it was executing, jump to the handler, came back here, and now it continues.
Yes.
Okay, perfect. Cool. I think with that, we are almost done, right?
Yeah.
I think so. Yeah.
And
Okay. And these are the
I would like to iterate that if you know only this much, right, about the Cortex M CPU, you are good enough for 70% of the cases.
Right. Right. Right.
For rest 30%, these are corner cases, and MPU has been one of the biggest problems for the ARM developers to handle.
Yeah. Yeah.
Creating some random behaviors. We'll look into MPU in a course that specifically focus only on Cortex M,
Okay. Okay. We'll dive into
and
the details.
dive into the details of how the MPU, what MPU does, and why MPU is necessary. Details, but for a programmer that doesn't have to work much on the CPUs, knowing this much
Mhm.
about Cortex M4 is good enough.
Right. This is sufficient. Fair. At least they can, self-navigate to a good degree.
Yes,
Perfect. Perfect. Okay. So next time on what do we have? We will talk about the linker. Fair.
we'll talk
Okay.
about the linkers.
Okay. So I think with that we can end the session for today. And for those of
Yeah,
you who hung around, thank you for hanging around and see you
yeah.
guys next time. Bye bye.